Okay, this is the last question, and I think this one might have been the hardest one, particularly the second part. We have here a mass spring system with mass m, and it is oscillating around position x0. It has a period t sub p and an amplitude a sub p, and the equilibrium position is x0. So then a second mass, just out of my picture here, a second mass of 2m is dropped upon it at the instant it passes through this equilibrium position. And it sticks to the top, and the two block system now oscillates with a new period, T PQ, and a new amplitude, A PQ. The first question asks to examine the numerical value of the ratio of TPQ over TP. So can we compare the periods of the larger mass system with the smaller mass system? Well, we've got a couple of equations here. I'm going to move this out of the way a little bit. Hang on. I'm going to move this up a little. Okay, we've got a couple of equations here where, in general, the period is equal to 2 pi times the square root of m over k. So for Tp, it's 2 pi times the square root of m over k, and for Tpq, it's 2 pi times the square root of 3m over k. And when we take the ratio of those two things, the 2 pi's cancel out. We've got the square root of 3m over k over the square root of m over k, and that pretty quickly resolves itself into just radical 3. So it's a radical 3-to-1 ratio where the period of the triple mass, 2m plus m, is radical 3 times longer than the period of just the single mass itself. Now, the last question is pretty challenging. It says here that the figure is reproduced, and how does the amplitude APQ of the two-block system compare with the original amplitude of AP of block P alone? So is it less than, equal to, or greater than the original amplitude? And it then prompts you to come up with a paragraph description. Okay, I think this is the hardest question on the whole test. There's a lot going on here: conservation laws, interplay between momentum and energy, and so forth. So let me walk you through my thinking, and you can kind of use this as an outline for a paragraph. Okay, so here's my thinking. First of all, the observation that momentum is conserved because the additional mass is dropped onto the first mass in a vertical direction, so that horizontal motion is not changed. And while it's true that the system has changing momentum as it goes back and forth, it goes faster at some points than at others. Right at that equilibrium position, it's got its maximum momentum, if you will. That's where its maximum velocity is. And while the spring and the mass are interacting with one another, the mass of the momentum of the mass will be changing. I think we can assume that that's just sort of an ongoing process, and the momentum at the equilibrium point should be conserved. So what's going to happen? Well, the mass will be replaced by 3 times the mass, and the velocity then must go down to 1/3 of the original velocity in order for the momentum to be conserved. So 3 times the mass, but 1/3 the velocity. So the product mv at that equilibrium point shouldn't be any different. What's the implication of that? Well, now that has an implication in terms of kinetic energy. So while its momentum is the same, its kinetic energy is now actually different. The maximum Ke, again, right at that equilibrium point, is 1/2 m times v squared, and that maximum kinetic energy must be going down. It goes down by a factor of 1/3, and here's how, right? The mass goes up by a factor of 3, but the velocity goes down by a factor of 1/3, and that gets squared. So that's 1/9 times 3, or 1/3. So the kinetic energy has gone down, the maximum kinetic energy has gone down by a factor of 1/3. And that has yet another implication, and that's this. If the maximum kinetic energy goes down to 1/3 of its original value, then the max potential energy must also go down. I think I want to change this word from by to 2, okay? Because it's not going down by 1/3, it's going down to 1/3 of its original energy. So why is that? Well, if the maximum kinetic energy is happening right at the equilibrium point, then the maximum potential energy must be happening at either extreme, wherever the amplitude of the motion is greatest. So that potential energy is elastic potential energy, which depends upon or is calculated by 1/2 k times x squared, where x is the stretching of the spring. And since we're talking about the maximum potential energy, we're talking about here as the value of x, which is the largest that the spring gets stretched by or compressed. And in fact, that's what we call the amplitude, right? When we the furthest it gets stretched horizontally becomes its largest value away from the equilibrium position. So the potential energy goes down to 1/3 of what it was. That means that the amplitude now must be 1/3, somewhat less than the amplitude it was originally, and I would say it would be 1 over the square root of 3 times smaller. So if we go back to the question says, what happens to AP? Is it, APQ? Is it less than AP, equal to AP, or greater than AP? And I would say it will wind up being less than AP by a factor of radical 3. So that completes question number 5. Again, that's a tough one, a really difficult one, with a lot of thinking to it. I hope that you have found all of these solutions to be helpful. Please come see me if you'd like to talk about any of them in greater depth. Take care.